Hello. In this video, we're going to do another Fermi estimation problem. This time we're going to talk about the UARS satellite that was launched by NASA in 1991. It had a 14-year mission, and by 2011, it was due to crash back to Earth. And so the question is, how worried should we be? Or how worried should NASA be that someone on Earth might get hit? And so that's the real world question that we want to estimate is, what is the probability of someone on Earth being struck by the satellite? Now, we're going to go through the modeling process. Even though this is an estimation problem, we can combine the two ideas and practice both. And the first step, as you recall, is to define the problem. And as you may remember, the first step of defining the problem is to brainstorm all the variables, all the things to think about to go with this question. So I encourage you to pause the video and do that brainstorming on your own, and maybe even see if you can work out the probability if you prefer. And then we'll come back and compare answers here in a moment. All right, so here's some variables that came to my mind. So first of all, the size of the satellite seems pretty important. The number of people on Earth. The distribution of people on Earth. Warning time. Would there be a chance that if the satellite was coming down a certain area, an area could be evacuated? And if so, how big of an area? The path of the satellite. And notice there's a lot of things that could be considered there. The speed, the direction, the trajectory downwards. So many variables here. To go into more detail. How would the weather affect this problem? And then what about the satellite breaking up? Is that expected? And if so, how would that change the answer? Now, as you recall, in this stage of the modeling process, we want to keep things simple. And that's part of the spirit of Fermi estimation, is we're doing a simple first step into this problem, and then if we find our answer unsatisfying, then we can go back and do a more sophisticated approach. And for that reason, we're really going to clean up most of these down to just a few key variables. It seems like we really do need to know the size of the satellite, and we do need to know the number of people on Earth. And those two things aren't that hard to research. The distribution of people is complicated. Warning time is unclear. The path of the satellites and the weather and the breaking up, we're going to ignore all of those. Now, at the end, we'll talk about a model that incorporates all these things and compare answers. But for now, let's just focus on these two ideas. And technically, we'll make an assumption on this third variable. So we're going to assume then that the satellite won't break up, and people are equally distributed around the world. All right. We also know, if you were watching the news in those days, it was clear that the size is about a school bus. And the population at that time was about 7 billion people. And again, we don't need to be any more precise than to the nearest billion for this type of problem. And so just for the sake of completeness, since this is the define the problem stage of the modeling process, let's go ahead and rephrase our problem into the following. And that is, what is the probability of a school bus-sized satellite randomly landing on a person if all people are spread evenly throughout the earth? All right, so that is our newly defined problem, and we're ready to go on to the next stage. So let's try to build the model. So here's where we'll use our Fermi estimation skills. So first we need the size of a bus. And we need to estimate that. And in fact, we only need to estimate the largest side. And buses seem kind of rectangular, so this won't be too bad. Maybe the front is somewhat square. And again, we only need one significant figure. And so I'm going to assume, or estimate, perhaps is a better word, about a 10-foot by 40-foot side. So in other words, that works out to 400 square feet. Because it seems like a bus is a little taller than the average person, and it seems pretty long. I don't know, is it 30 feet? Is it 50 feet? Is it 20? I'm not sure. Again, we could do a geometric mean sort of thing, but I feel like 40 it's not that hard to estimate the size of a bus, and so I feel confident that we're certainly within an order of magnitude, if not much closer, with that number. All right, what about the surface area of the Earth? Now, this is an example where we could look that up. That's a well-known piece of information. But just to get some more practice with Fermi estimation, let's say we try to do it on our own. And if we want to figure out surface area, we really need to know the radius of the Earth, or at least the circumference. And that's not so obvious how one would just guess that. We could try to do an interval estimate, but that's a little bit unclear what would be an upper bound, since we may not have a good feel for that. So let's think about something that would be simpler to do, and so let's scale it down. But how would you scale the circumference of the Earth? Well, one option that comes to my mind is time zones. So of course we know there's 24 time zones, because they have to make one day. So we know there's 24. And so now we just need to know what's the width of one time zone. And they're not perfectly drawn, right? There's zigzags here and there. But we know that generally speaking, it should average out. And so we need the width of a time zone. Again, we're just looking for an order of magnitude. Now, if you know how far across the U.S. is, that might help. If you know and how many time zones there are, that would help. Another way to think about it is to use an interval estimate. So if you do much driving across the United States, you know that you encounter time zones once in a while, but not very often. And so it's certainly more than 100 miles, but definitely less than 10,000 miles. Right, we can be safe in assuming that the width of a time zone is somewhere between there. And again, if you know a little bit more about the US, you might be able to zoom in on that value better. But for our purposes, we'll use this, and we'll use the geometric mean, which again, the geometric mean is, I'll go ahead and use the scientific notation way. So the square root of 10 squared times 10 to the fourth is the same thing as the square root of 10 to the sixth, which is the same thing as 10 cubed, or 1,000 miles. Which means that the circumference of the Earth is approximately 24,000 miles, since we have 24 time zones. But what I really want to know is the radius of the Earth. And since the radius is just the circumference divided by 2 and divided by pi, pi is about 3, so that's dividing by 6. So 24,000 divided by 6 would leave 4. So 4,000 miles. Now, we actually got lucky on this one. If you look it up, the equatorial radius of the Earth is about 3,963. So we probably got luckier than we deserve on this particular estimation, but that is one thing about Fermi estimation, and sometimes some estimates are too high, others are too low, and they average out, and you might get closer than you expect more often than not. So now that we have radius, we can calculate surface area, which we know is 4 pi r squared. All right, and so 4 pi r squared is going to be, let's see, 4 pi times 4,000 squared. And keep in mind that is in square miles, but our bus is in terms of square feet. So if we're going to match these up, we're going to need to convert square miles into square feet. Well, let's see, what do we have here? So we have 4 squared is 16. 16 times 3 is about 48, which is about 50. 50 times 4 is about 200. So this is about 200 times 10 cubed squared, right? Or what's the same thing? 2 times 10 to the 8th. All right, and that's still square miles. So the surface area of the Earth is about 200 million square miles, and now we want that in square feet. So 2 times 10 to the 8th square miles times, so I want miles down here, and remember we said feet, there's 5,000 feet in a mile, roughly, and I can square that number. And so then if I work that out, that is 2 times 10 to the 8th times 25 times 10 to the 6th, because I'm cubing, or I'm squaring 1,000. So that is 50 times 10 to the 14th, because 8 plus 6 is 14. And now we have something in square feet. So we have about 5 quadrillion square feet, and I have a satellite that's about 400 square feet. And so one way of thinking about this is how many school bus sized plots of land are there on the Earth? All right, and then divide that. So we'll divide this number by the 400. So the number of school bus size plots of land is 50 times 10 to the 14th divided by 400. And now we're ready to find the probability of the satellite hitting someone. Now keep in mind, this isn't the probability of it hitting me particularly, or one particular person. It's the probability of it hitting someone on the Earth somewhere. So the probability of a hit then is just going to be the number of people, so 7 times 10 to the 9th, divided by the number of plots of land. So in other words, how many plots of land are there and how many people are there to fill in those various plots of land? And so if we do 50 times 10 to the 14th divided by 400. So since I have a fraction within a fraction, I'm going to bring this up here. So that's 4 times 7 is 28 times 10 to the 11th, because the square root and the 9 make 11. And then down here I have 50 times 10 to the 14th. And then notice everything is bigger on the denominator, so I'm going to leave a 1 up here. and then 28 divided by 50, that's roughly 2. So that's 2. And then 14 minus 11 is 3, so 10 cubed. This is an approximation again. So about a 1 in 2,000 chance of someone on Earth being hit by this satellite is our very crude estimate. But notice the nice thing is this is an upper bound because we know that people are not equally distributed on the Earth. There's a lot of oceans and deserts and things where if the satellite lands there, no one's going to get hit. And so the probability we expect to actually be somewhat less than this number. Now, the sad news is that means that the other plots of land are more likely to have more than one person in it. So if a satellite does hit a populated plot, it's probably going to hit more than one person. But that wasn't the question. It was just a question of what's the probability that at least one person gets hit. And we have an answer of 1 in 2,000. Now, the question is this useful, right, if we want to analyze the model? So this is where NASA could ask themselves, all right, 1,999 times out of 2,000, the satellite is not going to hit a single person. That means that the actions taken to stop the satellite from landing on the Earth would not be worth it if that action was going to be prohibitively expensive or if it might cause other dangers. So like shooting a missile at it to knock it down might actually be more dangerous than the risk it poses on its own. Another way we could analyze the model would be to just compare it to other research. And so NASA did do a sophisticated simulation where they did take into account these other variables. So they did work out, well, because they did know the rough trajectory of the satellite and of course, where people were and so forth. And I don't know the details of their simulation, but they did take all that into account. And that simulation came up with a probability of 1 in 3,200, which notice is a little bit less than the probability we came up with. But we did ours in just a few minutes. So that's the power of Fermi estimation, is it can often give you a nice ballpark number without a lot of effort. One more thing though, if we wanted to report the results in this case, so this is all fine, but what if I am personally wondering about this? Would I be worried? Would I want to stay inside or live in a cave or something until this lands? So first of all, remember this is for the entire Earth. If I want the probability that I personally will get hit, then I can multiply this denominator by 7 billion. So now my probability of being struck is really low. And if I compare that to other known things, for instance, say getting hit by lightning, the probability is actually much less than being struck by lightning. In fact, it's been reported that being struck by lightning probably at least 1 million times more likely than being hit by this satellite. So there's really no reason for me to worry, but it might be interesting to follow the path of it just out of curiosity. So that's another example of Fermi estimation, and that's it for this section. We'll see you in the next video.